Welcome to Arctic Frontiers 2026. It's a privilege to mark the 20th anniversary of a forum that over 2 decades has built bridges between science, policy, business and society. From a small conference, Arctic Frontiers has grown into a global meeting place for dialogue about the future of the Arctic. This year's theme, Turn of the Tide, reminds us that we are living through a moment of transformation. Across the world, tides are shifting, in geopolitics, in climate, and in the ways we choose to cooperate. The Arctic reflects these changes more clearly than anywhere else. As ice melts and new routes open, and as attention and interest move northward, we are called to answer new questions about security, sovereignty, and sustainability. But changing tides also bring possibility. The Arctic has long been a region where shared interests outweighed conflict. Collaboration has shown how knowledge can build trust, even in uncertain times. Today, global tension challenged that trust. Some nations scale back research cooperation, confidence in international institutions is weakened. Yet many of us continue to believe that knowledge about the environment, societies, cultures, economies, and about each other is essential for rebuilding dialogue. The tide is turning. As we look toward the next 20 years, let us work to ensure it turns towards resilience, peace, and sustainable growth for the Arctic and for all who depend on it. Thank you for being here. May these days of Arctic Frontiers inspire new ideas, new partnerships, and renewed hope in what we can achieve together.
Arktis får stadig større oppmerksomhet, men overskriftene er ikke alltid de vi ønsker oss. Vi vil bidra til å endre dette. Vi unge er ikke bare framtiden i Norden. Vi er en del av nåtiden. Og vi lar oss ikke stoppe av grenser. Vi ønsker dere fine dager i Tromsø, og en vellykket konferanse. Og håper at dialogen her vil bringe oss nærmere et steg i riktig retning.
Welcome. On behalf of the Sami Parliament, it is my great honor to welcome you to Sápmi and to Arctic Frontiers 2026, Turn of the Tide. As a representative of the Sami people, I am proud to congratulate all of us on the 20th anniversary of the Arctic Frontiers Conference. This reflect on the lives we lead along the coasts. Tides, high and low water, and also form essential conditions for the Sea Sami culture in the fjords and coastal regions. Arctic Frontiers takes place at the same week as the Sami Week in Tromsø. With the Sami National Day on February the 6th, the festival celebrates Sami culture, sports and business with events such as reindeer racing, yoik, handicrafts and markets. I hope you get the opportunity to experience some of this. I look forward to valuable discussions and networking during these days at the Arctic. Gito.
Welcome to Tromsø. You have arrived in the Arctic capital, and I am so pleased to welcome you here for the Arctic Frontiers Conference. Did you know that we have another capital label going on this year? Tromsø is the European Youth Capital in 2026. This will be an amazing year where we put our youth first and foremost in every issue. Tromsø is a young and vibrant city with half of the population under 35 years old. I am the deputy mayor in Tromsø, and I am myself 25 years old. The project is called True North and is truly important for us now and in the future. I want you to ask yourself, what do you do for youth today and in the future? Enjoy Arctic Frontiers and enjoy Tromsø.
The Arctic, a home between ebb and flow, between high tide and low, between progress and setback. When the tide withdraws, tensions and conflicts are revealed. When it returns, power and stakes pursue. Power, counterforce, east and west. Growing interest from the outside. Arctic was perceived as the dark side of the moon, now a geopolitical hotspot. Ice melts, climate and global focus change. Floods, droughts, migration, cooperation, defense, resilience. The ice shrinks, new passages open. Trade, transport, control. Those with power over the Arctic have the upper hand. But there is a moment when everything is at rest. The turn of the tide. The moment between ebb and flow. Brief, but regular. The Arctic opportunity. We must dare to seize it and use it wisely. For respect, knowledge, and cooperation. The strongest is the one who stands alone, writes Henrik Ibsen. Not here, not in the Arctic, not in 2026. Welcome to Arctic Frontiers, Turn of the Tide.
Hello everyone to Arctic Frontier and welcome to the first science session about permafrost change in the Arctic. I'm Markus Engelhardt from the Research Council of Norway. I had the idea for this topic and I'm glad that so many abstracts come about permafrost changes. It's really a hot topic. And now I hand over the mic to Hanne Christiansen, who will chair the first science session.
Thank you, Markus. And welcome everyone again. A little technicalities before we get started. So we have very impressively 2 sessions on permafrost this morning. And this very first one is packed and full, and we will overrun time a little bit because of this nice introduction. But the second one, we actually lost our keynote speaker. So we will do the following. We will have all our oral presentations as planned, and then we will have a question and answer session in the end. And that means that you should actually, if you have some burning questions for the speakers today, consider coming in the second session, and then we can have a discussion in the very end right before lunch. But no further details, but it's a warm welcome to Professor Sebastian Westermann from University of Oslo, who is going to give us the keynote of the permafrost sessions today. And Sebastian is talking about modeling. Welcome.
Thank you very much. Can you hear me on the microphone? Yes. So I will talk about an initiative by the European Space Agency. It's called Permafrost CCI, standing for Climate Change Initiative, where we do global scale mapping of the permafrost thermal regime. And this is a big collaboration between different institutes, some of them from the University of Oslo, but it's a really European consortium running this. So first of all, when we try to measure permafrost, quantify permafrost, it's actually quite difficult. So the real definition is that permafrost is ground material that remains below 0 degrees for a certain amount of time. 2 years is something like the ground temperature, the thickness of the seasonal thaw layer, but then also a lot of like look into where is permafrost geographically, permafrost extent. The problem really when you want to detect it, especially from space, is you have very little indications from surface features. So here is 2 pictures which look relatively alike. Would you see if there is permafrost? I mean the foreground, not the glaciers in the background. So I would say it's relatively difficult. So the answer is like in one there is permafrost from what we know from the climate and from the maps, and in the other one it isn't. But from the surface they look actually very similar. So what can we actually do in order to detect the permafrost thermal state? And what we use is a time series of remotely sensed land surface temperatures. So essentially you monitor from space the temperatures over a time. And then we can use a model to project these temperatures further down. And if the temperature is below 0 degrees, then there is permafrost. Otherwise, there is no permafrost. So it actually requires a combination of a numerical model, which of course has its uncertainties, and remote sensing, which also has uncertainties, obviously. This is how it looks like, what we need. Yeah, so here I have to take a moment. So here we have basically our model grid, which goes into the depth, and here is the time axis, and then we have, for example, a seasonal snow cover build up, and in between this is where we have our temperatures that are measured from satellites at a resolution of something like 1 kilometer. But then we have to basically project these temperatures when there's snow cover, like outside. Of course, they measure the temperature at the top of the snow cover. We have to account for the insulating effect of the snow cover, so we have to know how much snow there is. The properties of the snow cover are changing, so we have to account for snow properties. And then finally, like what's below in the ground also matters, and this is relatively difficult to quantify from a satellite as well. So we have to make assumptions over all of these, but if you then basically solve the heat conduction equation, you get time-resolved depth profiles of temperature, which you then can further evaluate. Here in this case, we use MODIS land surface temperature. That's a satellite that's available since the early 2000s. And then we use various remote sensing data for the characterization of snow and the ground itself. And what we get is 1 kilometer resolved products. The official products are from 1997 until 2023, but this is to be continued. Ground temperature at defined depth, yeah, so something, for example, what's the mean annual ground temperature at a certain grid cell at 2 meter depth, at 10 meter depth, etc. We get the active layer thickness, the thickness of the seasonal thaw layer, and also permafrost extent. I will come back to that in a second. So what we see here is here you see an animation that's a 2 meter ground temperature, and up there it's the year running, and it's the difference from our first full decade. And you see like the further this is now going into the 2020s, the more the yellow ones, which is more higher temperatures than we had in the first decade, are emerging. I just quickly go back. So you see in the first decade there is actually still quite a lot of deviations in both directions, but on a very large scale here in Eurasia, actually temperatures are way above average in the last, especially the last something like 5 years. Yeah? So you really in this product, although there is some regions which have even a net cooling, yeah, but in almost the entire area, permafrost is warming very strongly. We can quantify this here. This is a bit more difficult graph. So what we've plotted here is the spatial statistics. So basically, like up here, this is the warmest temperatures we see in the permafrost domain. This is the coldest temperatures we see in the permafrost domain. So that could be, for example, somewhere in northeastern Svalbard, or here in North America, or for example, northeastern Greenland in some of them. So this is where temperatures are like -10, -12 or something, and this is the 90th percentiles down here, 75 percentile. So the black line is the median, so sort of the most typical temperature. And when you look at that, you see quite the strong changes over time. You also see that the cold temperatures are increasing much more than the warm temperatures. The reason here is that for the warm temperatures, they're already very close to zero. So any sort of temperature change is buffered by the melting of ice. You also see that there is a somewhat different trend for North America, but there it's mainly like the distribution of the land masses, which lead to a slightly different statistics. Look at that for Svalbard. This is just like an example. Here, this is 10 meter temperature shown. You see this very, very strong increase, something like more than 2.5 degrees in the the last 20-something years. When you compare that, for example, to one of the terrestrial monitoring sites, I will come back to that. This is the borehole on Jansenhaugen. You see, this is just like a single site. Yeah, so of course, this is one, in a way, grid cell that is contained here, but at least roughly, yeah, you see that this is a little bit colder than that one, yeah, which is not a contradiction, but at least roughly we can represent the overall temperature development that is actually also measured on the ground, although, of course, there is a lot of spread in between. What happens when permafrost thaws? And this is like in reality, basically you develop like an unfrozen zone. Yeah? So essentially like the ground will not freeze everywhere again. And we now have to think about what is actually happening in these models and how can we represent this. This is a non-trivial case because of course, if you just have a single model realization and you have a 1 square kilometer, the model tells you permafrost disappears at one point in time for an entire square kilometer. But that's absolutely not what's happening. Yeah? Because the problem is within areas of 1 square kilometer, which is, for example, sampled by a single borehole, as we just saw, yeah, there is quite some temperature spread. And we account for this by not running just like a single realization for a 1 kilometer pixel, but several, in our case 7. And what we account for is the subpixel variability of the land cover, which we translate to changes in the ground thermal properties, and to some subpixel variability of the snow cover. Here you see a picture of how the snow looks like around Longyearbyen. So there's places with a lot of snow where permafrost temperatures tend to be quite warm, and there is places with very little snow where permafrost temperatures tend to be quite cold, and we apply some sort of probability function how in which terrain this is likely. So the final products that we're giving out, like the ground temperatures I showed you, this is also actually the median over all the 1 kilometer ensemble. Yeah? So within this 1 kilometer ensemble, we also get several temperatures. And this can be a spread of easily more than 5 degrees. Compare these 5 degrees to the absolute temperature change. This is significantly more in some areas than we have a spread in the temperatures. Which means, of course, that when permafrost actually thaws, some of these ensemble members will thaw first, and then we see a reduction in basically the fraction of the grid cell in this case, which is represented by permafrost. So here is an example. This is for Svalbard, where this is mean annual ground surface temperature. This is a measurement. Yeah? And you see most of them, or pretty much all of them, are below 0. So this is in a more or less continuous permafrost area. And this is our model ensemble. This is that year. This is ground surface temperature from the model. And you see that there is up to a 4 or 5 degree spread in there. Yeah? So this is at least the range is roughly represented. Maybe not entirely the distribution, but here what would happen is that the very first, the warmest one would thaw first, and then there would be a reduction in the permafrost fraction. Or here, this is Finnmark, something like 250 kilometers to the southeast from here. This is a peat plateau. So there's permafrost here, no permafrost there. And here in our model realization, we see that for wetlands, for a wetland class, we actually have like permafrost, temperatures are below 0, but when we have some sort of a shrub class, which would be something like that up here, it's none. Yeah? So with this, at least if the land cover classification is correct, we can represent that and also get the fractional permafrost. When we look at that permafrost extent, here this is an animation going 20 years back in time. So you see, not huge amounts are actually happening in this case. So this is much less spectacular. Here, the intense colors, this is where there's a permafrost in all our ensemble members. So this would be something like continuous permafrost. And then it slowly sort of fades out. This means that there is less and less permafrost per grid cell. And there is, if you look at it, it doesn't look very spectacular, but there is a real significant change going on. This is an area, so when you look at the difference here of something like a couple 100 kilometers, that there have been actually thaw processes going on. And you can quantify that. This is now also a difficult figure. This is now since from 20 from the early 2000s to the second decade in the 2000s, what is the areal change per grid cell? Yeah? So this just tells us something like in a certain amount of an area, there is thawing going on to a very limited degree. Yeah, so this is in a very small part of a grid cell, there are thaw processes going on. So here we talk about like a 10% reduction or something like that, a 20% reduction. You also see some positive ones where permafrost is newly formed. This is usually very shallow permafrost. So in our model, we count permafrost even if you just have 10 or 20 centimeters that essentially survive between consecutive years. This is what's happening here. But you see that there is very little. And most of the change is actually not like that permafrost is disappearing at the level of a grid cell of something like 1 kilometer, but a very small fraction. And this is the important part, that permafrost is actually thawing on huge areas, but within these areas, only to a very limited extent, or disappearing in this case. Thawing is also going on in the others. So this you see, for example, as the warming, but this formation of unfrozen zones, and I think this is something that matches reality quite well. This is going on basically always like at the warmest places that like exist. They are pushed over the threshold, but then there are still colder ones and ones which already potentially have been permafrost free. But this is a very important part, that actually this talc formation is occurring over very, very large areas as we speak. So millions of square kilometers, that's actually quite a lot. This does not mean that millions of square kilometers of permafrost have gotten lost, but the impacts of this, and this is the iconic one that is in the media everywhere, this is these rusting rivers in Alaska. This is something that could exactly be explained by something like that water is finding new flow paths. For this, you don't have to get rid of all the permafrost. It's enough to get rid of some of the permafrost. And you can see that that can have like quite disproportionate effects. And of course, this is now a very spectacular, like poster child effect. But there's many other effects which are completely hidden. You wouldn't see that. So if this was not discolored, but for example, it contains some toxic ions or something like that, then it wouldn't be quite as much in the media, like if you couldn't produce these pictures. So many of these impacts are actually hidden, although they exist. So to sum up here, I'll have a bit longer outlook. The essentially fusion of satellite data and numerical models to some extent allows us to evaluate the impact of climate change on permafrost in the last something like 2.5 decades. Since we have these satellites, we're working on extensions a little bit back in time, but the earliest we can potentially do is something like 1980, not before, which is of course very limiting. And it's very important that this is meant to complement, not to replace, existing terrestrial networks. This is a terrestrial network of permafrost monitoring where there's boreholes, individual observation sites. And of course, at these boreholes, you know very, very well what's going on. This is important. At the same time, when you look at the spatial representation, there's areas where there is very little going on because it's so hard to get there, and there's simply no financing to make a borehole network that covers everything. So what we get from terrestrial monitoring networks is actually like when we just look at the rough trends and so on, it's all within the range. But of course, here in this case, we have basically like a true spatial representation, and at the same time, we have certainly a reduced accuracy. So this is not quite as good. And the two together, I think there's quite some potential to characterize that. What we could do is near real-time monitoring. That doesn't exist for permafrost. It exists for example, Arctic sea ice. You're used to seeing headlines. There was some sort of extreme summer or something like that, and it's in the news. For permafrost, this is usually coming with quite a time lag, which I think is, for the general public, not quite as satisfying. So this is possible, but so far we don't have an implementation, but this is a system that we are planning to bring further. So, for example, here, this is from the Norwegian news. Svalbard in 2023, record warm or something like that, and then some more. And this is what we would see, for example, for the active layer thickness. This is certainly not too correct for Svalbard right now, but you see this is basically doubling the yellow of the active layer thickness compared to like a reference year. So just from the visual, you see that something has been going on in that year. And you wouldn't see that, let's say, in 2020. So this is certainly like there. And for just like informing the public, this would be a possibility. Finally, and this is very important to keep in mind, how good is this data set really? So, because, I mean, it involves models, it involves remote sensing, there is lots of error sources. So, and this is now very important, it is designed to be statistically correct on the global scale, but strong mismatches do occur on the local scale. And the question is, are we actually happy with that? And I think as a conclusion, I could say we're like 80% there, but then the question is, should we do the remaining 20%? Can we do that? Because the figures I showed you, they will not change very much. So, and these last 20% are quite challenging. I can just show you a little bit like what we could do. This is Gaustatoppen in southern Norway. And here we, for example, run 5-meter mapping. This is the same crest here. This is the north side. So you see again like these purple colors. This is the permafrost. And this is something that, of course, in principle could be done also on the global scale, but it would be quite time-consuming, and we essentially have to make a completely new system in order to implement that. So it's not like we need 20% more work into that, but it's actually more like that it's a completely new process. And the question is, should we actually do that? Considering that the major global figures would probably not change very much. Thank you very much.
Thank you very much, Sebastian. We have time for a question or two. If we have anything going on in the audience. Yes, Keith? There may be a mic coming to you.
A very interesting talk. Thank you very much. 2 points, actually. If you would like to have more like a ground truthing, where would you sort of would that help you to make your model better?
Definitely it would. The point with the ground truthing is, in principle, we have actually quite a lot. But the problem is usually that, for example, if we have a single borehole and we don't really know where it is with respect to the temperatures around, then it's sometimes hard to falsify the model. So in many cases we can, but in many cases we're like 2 degrees off. And then it's like, whew, it could be right, doesn't have to be right. So there is, for example, networks that place a lot of smaller sensors around, like cheap ones, not so deep, like the ones I showed you. This is something that goes very much together with the model. And then, of course, finally, like extensions of this monitoring network, or even just continuation. So now, for example, with Russia, it's not so easy to get data. So would help a lot. So the most important point is like, let's say the financing for these terrestrial networks, this must be secured, and it's definitely not like because we can run models that we should reduce the efforts that we do in the field.
Thank you very much, Sebastian. I think we have run completely out of time, and we have a strict program, so that's for the question and answer session later on. We'll now move on to Abdullah, who will tell us a little bit about UAVs. So now we're actually leaving the ground surface and learning how we can observe permafrost from space. If we have a presentation. Yes, we will.
Okay, thank you. Today I will just briefly talk about the recent work that we did with UAV-based greenhouse gas flux quantification over permafrost ecosystem. I will keep short in here because Sebastian talked a lot about already about the permafrost, but the only thing that I would like to mention in here, this area is also stores huge amount of carbon. And the question that we are trying to answer at least is this region is going to be a carbon sink or carbon source in the future. So the motivation of this speech would be, you see the different carbon monitoring network tools in here, the flux chambers, eddy towers, and airborne eddy covariance. And they all have different spatial scales, from smaller scale to the largest scale. And also in between, because the scale separation between these network platforms are broad. And this is our first motivation was to use this UAV to close this scaling gap, and because UAVs can provide different spatial data at different scales. Another motivation we had to use these UAVs to investigate small-scale structures over these ecosystems and also try to quantify carbon flux over hard-to-reach areas. Because the landscape is very challenging in Arctic, you cannot just walk around or also installed eddy towers everywhere. And finally, we would like to combine all these three platforms you see on the right-hand side to provide a better, more accurate carbon facilitate policy making. This is the platform we developed. You see in this figure. So we have two gas analyzers on board for CO2 and methane measurements. We also placed an anemometer on top to measure wind speed and other environmental variables. And at the end, we have about 20 minutes of flight time with this platform, and we sample the gases at 2 Hertz, so 2 data points at 1 second. Up to now, we visited several field sites in Arctic. The picture you see is from Stordalen Mire, northern Sweden, which is a subarctic wetland. It's sporadic permafrost. This is from Trail Valley Creek, Small Bear Lake. It's a continuous permafrost zone in northwest Canada. And also, lastly, we visited a methane seep that is located in Mackenzie River Delta in northwest Canada again. You can conduct several flight techniques and apply different quantification methods to quantify the fluxes. Today, I will only talk about the curtain flights. And you see this sketch, how they work. Basically, you create this observational plane, and then you apply the quantification techniques I listed in here, which are most popular ones. The mass balance and the Gaussian Pulling immersion, and then you can quantify the fluxes that comes out of the source. So this is the real-world application of this sketch. You see the transect that was collected from UAV, and then the altitude that was covered. And what you see in the color bar is methane enhancement, and as you see, the closer to the ground, we have higher methane, and above it is background level. This is a video I get from the methane seep. So when we basically conducting that curtain flights over these methane seeps that is located in Mackenzie River, this is actually a geological methane seep, which is the ancient methane that is stored below the permafrost. And due to warming, the permafrost destabilizes, and then it creates the fractures. So the ancient methane is seeping out to the atmosphere. And then this is how we basically collect the data with the UAV. So you may think this is a rare form, but it's actually abundant in this region. According to the Limmer Atoll, there are other 60 seeps around this location. And in July 2025, we sampled one of them together with the environmental researcher from Environmental Research Canada. And we used 2 UAV platforms. This is our UAV platform, and this is from Environmental Research Canada. And we also compared the different sensing techniques, closed path that we use, and then open path from Environmental Research Canada here. This is how they look like from bird's eye view, the curtain flights. So from the green color bar represents the closed path sensors, and the red color bar represents the open path sensors. So in total, we have 4 curtain flights over this region at 2 different downwind distances. And we applied that 3 quantification methods that I showed earlier here. So in total, we have 12 different estimations. And on average, we concluded that this methane seep actually emits around 11.4 kilogram methane per hour, which is quite a lot. It is equivalent to 2.2 square kilometer of the biogenic fluxes surrounding this area. So this is only from one methane seep. And now we are currently working on to couple the curtain flights with some simple atmospheric transport model, in this case backward Lagrangian model. I took this sketch from Flesch et al., and you can basically see how this model works here. So you can consider that you collect concentration at the location M, and then you solve the Lagrangian to get this source area attribution. This is what we did in Stordalen-Meyer, and you see the source area from one of our curtain flights in here, and basically our idea to normalize the flux that is calculated from the curtains to get the aerial flux. Our end goal also to use all the curtain flights we conducted from the Meyer, from the Stordalen-Meyer, and then use some sort of like a regression together with the land cover classes and other environmental variables to get the surface fluxes of methane. And you see we kind of get the trend, which is from very preliminary results. So for example, the Fen has the highest methane fluxes compared to Palse and the lakes. And we also try to now validate this model. So you see the footprints from eddy covariance towers and then the curtain flights in here for 2 events. And in total, we have 4 events from our recent field campaign. And this is the comparison between the eddy tower and the UAV only for the CO2 fluxes. And you see the model is kind of promising. So sorry, the method is kind of promising. For the future works, we would like to include the grid flights as well. I used a simple atmospheric transport model as a term in here because we already conducted small-scale immersion using a more sophisticated model using larger dissimulation. And you see the surface fluxes from Stordalen-Meyer as well as a result of that. We also would like to now look into more detail with this geological methane seep to investigate the spatial and temporal variability since we have multi-year observations from this site now. Also, the main goal is to provide upscaled regional flux budgets together with all these 3 components of the carbon monitoring networks in here you see. With that, I would like to conclude my speech. Thank you.
Thank you very much for an interesting presentations. We have time for a question or 2. Yes. You will get a mic from this nice man.
Thank you. Very interesting. Can you hear me?
You just speak, and then it happens.
Okay. My question relates to both speakers. Putting the 2 together, do we know how long permafrost needs to melt before we have the flux happening?
I think from the spatial location, you can already see because some part, as Sebastian already showed, is already melted. Like we have this sporadic permafrost, for example, from Stordalen-Meyer. So we can measure that, and then I think we see that huge methane flux is coming out, at least at this time scale, because after permafrost melts, what you see is the wetland, but we don't know what will happen in the next centuries or so. Maybe it will dry out and you don't see that much of methane coming, but that is the question that we are trying to answer now with the measurements.
Any more questions? Or we will take we can also return to this because I think we will have some other presentations today that may actually help you answer this question as well. I have a little question for you. So you've shown these very nice curtain flights and so on, but how often are you planning to do this? I mean, if we are to use this as a monitoring technique, it's not once in a season, it has to have some regularity. Is that feasible?
Yeah, I mean, it is very early to say that, but it depends on also like the FAA's rules and stuff, the aviation rules. But I think we have the technology also to now fully automate these flights without any pilots in control. I think maybe in future you might be seeing the drones flights regularly over this area, like eddy covariance towers.
Thank you very much. Unfortunately, our time has run out. And then we will turn to some permafrost data. So we are learning about something that has just happened. We've seen the rebirth of something called the Global Terrestrial Network on Permafrost. And today we have Tilman Lübker from the Alfred Wegener Institute, who has been working on this, who's going to introduce us to that. Welcome.
Yes, thank you very much. So before I come to the GTMP data platform, I would like to say a few words about GTMP as such. GTMP is the global terrestrial network for permafrost, so we talk about in situ data here. The network was established in the late 1990s and is the leading international program for long-term permafrost monitoring. The mission of GTMP is to sustain a comprehensive global network that delivers consistent, high-quality, long-term observations of key permafrost indicators, and what those indicators are, I'm going to talk about in a minute. Now, the data we have in GTMP support the assessment of the current state of permafrost on a global scale, but also, and this is maybe more important, the changes over time. And as we've heard already today, there are a lot of changes in permafrost. And here on the map, you can see the stations we have in GTMP. Now, GTMP is also about people and the involvement of people, bringing people together. We have people in the network from more than 100 organizations worldwide, coming from more than 30 countries. And we regularly have workshops where we come together and talk and exchange ideas and see how we go forward. The structure of GTMP includes a steering committee, an office, which I'm also part of, and an advisory board. And we have a lot of national and young national correspondents that organize the work within their countries. You might have heard about GCOS. GCOS is the Global Climate Observing System. It is run under the WMO and other UN organizations. And GCOS has defined a system of 55 so-called essential climate variables. And these, of course, also include the cryosphere. And within the cryosphere variables we have permafrost. And here for the permafrost defined, and these are permafrost temperature, active layer thickness, and rock glacier velocity as a third quantity. Now, GTMP is not only delivering the data for these quantities, but also we are in contact with other observing systems, with the scientific community, of course, with the International Permafrost Association, and also other national organizations. Now, exactly 14 days ago, we finally launched a new data platform after a lot of work, many discussions, getting feedback from the community, writing many thousands lines of codes. And we used this opportunity to celebrate this a bit and also spread the word about this. So what is the data platform? It has several components. We have the front end, which is the gateway to the data platform. It's a website, open access. But then we also have a back end where a login is required to upload new data and maintain existing data. And we have an API database, and everything is stored on servers in the data infrastructure. Now, the front end, as I said, it's the gateway to all the information we have in GTMP. It's meant to be easy access and self-explaining. We have 3 different sections you can see here on the top. The Explore section is the start page. Here on the left-hand side, you have a set of global filters. For example, you can filter the data by permafrost zone or vegetation type. And then you have topic-related filters. And here in this example for permafrost temperature, you can choose different frequencies of data. And all these filters are linked directly to the map. So whenever you select something here, this gets displayed on the map. And then at any time, you can also switch between the map view and the table view, where we have some more detailed information also. Then in the second section, the view section, you get more detailed information. In this example, you have to see all the metadata for a borehole with all the settings and contact information, and also how to site this borehole. Then we also integrated a direct visualization of data here in this example. This is a visualization of active layer thickness data. You can browse through the different years and see how the changes happen here. And then if you figured out which data sets you want to download, this is all organized by a download card functionality, where you can then also filter your data again and, for example, set individual date ranges before you then start to download your data sets. Okay, in the back end, as I said, this requires a login. And here the users that are registered with GTNP can upload new data sets, edit all the metadata. We are using a lot of drop-down menus to have consistent vocabularies in the database. And we also established a help system which guides the user with every field he or she has to input into the database. We're also running data quality checks upon upload. So for example, we have a data preview that you can see, oh, here might be something wrong with my data. And then we have an error handling. And in this example, there are many no data entries. So the user can then decide to keep or delete these entries. Yes, the server structure is entirely hosted by the RV Computing and Data Center, and it was designed for long-term reliability and scalability. We also developed a new data model for the database and transferred all the information. It's still a bit complex. It has over 200 fields, but we reduced the complexity compared to the old system significantly. We are entirely using free and open source software, which I think was a good decision to make. And a bit more technical here, if you're a programmer and want to use the data in GTNP with your code for analysis, for example, you can access our API. There's more information here also on the website and code examples you can then use to programmatically access the database. We also introduced the system of persistent identifiers that provide stable permanent links to all the entries we have in GTNP, and that then resolve to the resources depending on the type of information you want to get. Okay, what's next? So for the data platform as such, in the beginning of next year, we will start to have yearly data collections, so-called products for downloads that will be stored in Pangea with a DOI, and all the co-authors that contributed to these data sets will be listed there also. We will continue our efforts to standardize Permafrost data in a subgroup of WMO. And the third ECV is still missing, here rock glacier velocity. We will integrate also into the data platform. And we are also looking forward to establish direct linkages to national data centers, for example, in Switzerland and Norway. And also we are planning to update the much-cited Permafrost is Warming at a Global Scale paper sometime this year or maybe next year. And given there will be funding, my colleague will lead an IPA action group on defining requirements for the spatial representation of Permafrost. And we very much hope to officially become a GCOS affiliated network sometime this year, I hope so. And also the involvement in the Permafrost shared Arctic variable is something we will continue to be involved in. Yes, and with that, I invite you to visit our website, which is also new, and the data platform, of course, and please provide us some feedback. Yeah, I'm looking forward to hear from you about this. Thank you.
Thank you very much for introducing the new version of GTNP. Do we have any quick questions? We can have time for one quick one. Maybe I can just ask you a little bit about this annual production of data. Do you want to say, what is that going to be, something that just sits in Pangea, or is it useful for BAMs and these other assessments on an annual basis?
Yeah, we also have BAMs on the horizon. We want to actually automate some of these processes to have overviews of what's been going on to do this in an automated way. And with these data products, we also want to provide an easy way to download all the data within 1 year. And then this gets stored permanently in the Pangea repository. And we will also offer continent-wise data products and also aggregated to daily values. Because most of the data that is actually there is like sub-daily, hourly data, for example. And maybe for global assessment, this is not so relevant, so it's easier for modelers to use this data.
Thank you very much. And then we will move on to a different theme, but we will go back to Sweden and Stordalen. So we have Natalie Tries, I'm probably not pronouncing this the right way, sorry, from the Max Planck Institute, who's going to talk to us about different gas fluxes coming out of the permafrost and some measurements that you have been doing in northern Sweden. Welcome.
Okay, I guess this is my height now. Welcome, everyone. Also, from my side, I will talk about these temporal and spatial dynamics of methane, so CH4, carbon dioxide, CO2, and N2O, which is nitrous oxide, in a thawing permafrost peatland in northern Sweden. Just very briefly, Abdullah actually introduced that already. Why are we doing this? This is, of course, because of global warming. We want to know what will happen in the Arctic in the future. Is there going to be a source of carbon? Is there going to be a sink of carbon and also nitrogen? And is there a tipping point that we have already gone over or will go over in the future? As announced, we will go back to the Stordalen Mire. This is, I don't know, maybe 4 or 5 hours away from here by car. It's sporadic permafrost, and we added 24 what we call chamber base positions. So this is basically a plastic, so PVC collar that you put into the ground, and we left it there for a few years so we could always go back to the exact same spot. And then we did in total 5 months of field campaigns in the more or less snow-free season between May and September 2022 until 2024. What we did is we used the so-called chamber technique. So you can see that chamber here. You can imagine this is just like a rubbish bin that you put onto the ground, and then you can measure the concentrations that are either going into this chamber or going out of this chamber over time. We did that with portable gas analyzers. So these are basically devices that you can take into the field, and then you see real-time online measurements. This is for N2O, the other ones are for methane and CO2. And we wanted to do that in different light conditions to then also see the impact of PAR. PAR is photosynthetically active radiation. So here we added this cover on top that will reflect the daylight so we can see what would happen in the dark. We also did these measurements along a so-called dry to wet gradient. So on the left side in these brownish plots, we call them palsa lichen and palsa moss. You can imagine this is quite dry. On the lichen, there's not much vegetation apart from lichen. Palsa moss would then cover all the mosses, all the shrubs and things like that, just more vegetated if you like. And then on the right side, it gets a bit more wet. You have the bog where you have the peat-forming mosses that store a lot of carbon. And you still have them here, but also a little bit more cotton grasses, for example, in the fen. Just wanted to show you what our spatial resolution was here. So we added 2 of our transects really close to each other. This was because it's in the so-called footprint of one of these eddy covariance towers that Abdullah mentioned. And then one a little bit further away in an area that is not so disturbed. And you can see these are really close to each other. So here's the scale. And this is kind of important to know, like, as those who were in the Arctic already know, when you look at it, we saw it on pictures as well, it all looks very different. So we try to actually get these different spatial heterogeneity, even though our plots were kind of close to each other. Okay, now we go into the results. This is a bit complicated in the first part, so I'll try to explain it. Down here, you see the months of the different years, so May, June, July, August, September. And then here you always see the flux. In this case, it's now the methane flux. And then we have these separate boxes, and these are these different vegetations or microhabitats that I introduced before. So palsa lichen, palsa moss, bog and fen. Then you have N, which is the number of measurements, and then these significant values, and S would be not significant. So anything that has a star is significant. The more stars, the better. And NS is not significant. And I think it's very obvious here. What you can see on the very right is the fen. And there you have, compared to the other microhabitats, really, really high methane fluxes. This was expected, so no big surprises here. What you also have here are the light conditions. So these box plots that are in orange, they show the light conditions, and the dark ones are the ones you measured excluding the sunlight. And here you can see that only for actually the May measurements there was differences in these methane fluxes. Just quickly have a look at the scale. Here we go from 0 to 30. If we zoom in a bit, so we go from 0 to 3, still for methane, we can finally see the other fluxes. So still, compared to the pulsar, the bog fluxes are quite high, but already much slower than the fen ones, lower. And then here, you can see this dashed line, and what we have below is uptake, and what we have above are these emissions. So you can see that here in the pulsars, you actually have some small methane uptake. So the methane is taken from the atmosphere and stored in the soil. You can also see these dots, so these outliers, and that means that apparently in spring something is happening, maybe because of the snow melt or the permafrost melt, we have some outburst of methane that makes these pulsars a little bit wetter. We now continue with CO2, same kind of graph. Here, important to know what is light is the net ecosystem exchange. So in that you would, for example, include photosynthesis, and the dark is the ecosystem respiration, so that whatever comes out of the plants and the soil into the atmosphere. And you can see that there are some differences. Fluxes aren't very high. They get a little bit higher with pulsar moss and even higher in bog. And now here we have some vegetation, and you can see now on these stars that the differences between light and dark measurements are significant, and this is also what you would expect for CO2. So everything that is again below the zero line will show that CO2 is taken up. This is of course because of photosynthesis. Plants are taking up CO2, and then here the soil is respiring CO2. And then the last, but not least important, N2O flux. Here again, same kind of graph. You can already see that there's some kind of seasonal pattern with highest emissions in May and September, and you can also see that there's significant differences between light and dark. This picture is very similar, and it goes on like this. The only difference you can see is that these fluxes appear to get bigger. So the uptake is higher, but also the emissions are higher. And so here it's important to see that there is this seasonal pattern, which was not observed like this before in these permafrost regions. And also here in fen, we get these largest differences between light and dark fluxes for N2O. To conclude, for methane, we saw that fens released the highest amount of methane, which was expected. This was especially the case in summer and autumn. And for the pulsars, we did find a small outburst in spring, but generally they would take up methane. For CO2, the fluxes were highest in July because the plants are very active and there is light-dependent uptake, which is predominantly happening where we do have plants or mosses doing so. And then for N2O, we found highest light-dependent emissions in pulsars, and we found that in shoulder seasons, so in May and September, and generally larger fluxes, so both ways, either emissions or uptake in bogs and fens. Thanks a lot for your attention.
Thanks a lot for your presentation. Do we have questions? We have time for one. Yes, Sebastian?
Oh, sorry.
The high methane emissions from the fen, do they have anything to do with permafrost carbon, or is this just like from the modern vegetation that has regrown there?
I actually don't know yet. So I saw that we then also did a random forest analysis, and their vegetation definitely had the highest impact. So I would say more from vegetation, but I would still have to look to what extent the permafrost had an impact there.
Do we have any quick ones? Yes, here in the front.
Yeah, I was wondering about the nitrous oxide difference between light and dark measurements. How do you explain it, or what's the rationale behind it?
Hard question. So the exact answer I can't give you, but I think it has something to do with vegetation and microbes. And yeah, the paper will come out as soon as I have the answer, but we can also talk about it later.
Thank you very much. I think we will not spend more time.
Yes.
You can come back to questions. I think it's also relevant later when we've heard more presentations. So we will move on to the next presentation, which is given by Judita Aga, who is from the University of Oslo, and we will now go back to Svalbard and learn something about mass movements in warming permafrost. So we'll get insights from ground temperatures in Svalbard. We look forward. Welcome.
Thanks, Hanne. And thanks for the opportunity here to present the Arctic frontiers. I will talk today about mass movements involving permafrost, and as Hanne said, present a case study from Svalbard. And this work is today presented by me, but the colleagues from NGU in Norway and BGR in Germany contributed as well. So you have seen that map before, the extent of the permafrost in the northern hemisphere, and this permafrost is warming, resulting in increased ground temperatures and the deepening of the active layer. And today I will focus here on Svalbard. And also here, the permafrost is warming following this global trend. So just like one example from a borehole, you have seen exactly that borehole from Sebastian before, where the permafrost is warming by 0.8 degrees per decade since the last 25 years. Svalbard, or large parts of Svalbard, are covered by glaciers, but where there are no glaciers, the landscape is very scarce with very little vegetation, and you see that Svalbard is quite mountainous. So we have rather gentle slopes, but also very steep mountain areas. And now in recent years, we see that lots of these slopes begin to destabilize. So we see a lot of new debris flows, active layer detachment, but also two large rock slope failures that happened in recent years. And now in the first part, I want to focus on these rock slope failures that you see here. Where's the field site? So we are at the Forkastningsfjellet. That's about 9 kilometers distance to Longyearbyen, which is the main settlement on Svalbard. And you see that this mountain range of Svalbard, it's divided into distinct landslide blocks that you can see here in different colors. And these blocks are slowly moving downhill with a few centimeters per year. And for a long time, that was what was happening. So they were just slowly moving. But then two failures happened. So the first one in 2016, you can see here the deposit. It was 175,000 cubic meters, and it came a little bit of a surprise, so we didn't have like any field data prior to this event. But after that happened, we started the field campaigns and documented that failure. And then a few years later, in 2022, the next block failed, just right next to the one in 2016. That was larger with 750,000 cubic meters. And here we had a field campaign just a few months before this failure happened. And we saw signs of destabilization prior to this event. For example, we measured the surface displacement of this block. And that was in that year 12 centimeters, or almost 12 centimeters. And that was an acceleration to the previous year. So we measured the surface displacement for like since 2017, so after the first failure. And then just the year before it failed, we saw this acceleration. We detected the sinkholes here, and here this was then the failure plane of this landslide blocks. You see that this was opening up. And what we saw is that water was infiltrating into the sliding plane. And that is important to note because typically the ground should be sealed for deep water infiltration. So the subsurface water flow should be restricted to the active layer. But here the water was just disappearing into the failure plane and then reappearing at the coastal face. So kind of down here when this block was still up there. So there must have been some hydraulic pathways along this sliding plane. And that hints, of course, towards that there is some permafrost degradation along this sliding plane. And now some more recent pictures from the field. So how does the situation look like today? So here these pictures are taken from this, behind this next block. And we see that there's this little creek cutting where the potential failure plane would be of this next block. And we see that there are cracks opening here parallel to it. And we see that the water from this little creek is again infiltrating into the subsurface. And we see that water is reappearing here at the coastal face again. And that was during a rather dry season as well. There was still like water coming out of this coastal face. So it looks like this block here is as well destabilizing. But we couldn't detect any like acceleration of the surface deformation. And this block is much larger than these two blocks here before. So we can't really say if a failure will happen or when it will happen. So we documented these rock slope failures over the last years, and while we were doing it, we were also documenting debris flows and active layer detachments at this field site. So you see here, for example, there are lots of them coming down on that hill slope. And when we're looking at that, of course, there are some questions arising. So, for example, which role plays really the permafrost in the destabilization of the slope, especially for the large rock slope failures, and how will the permafrost warming on Svalbard affect also the landslide occurrence in the next decades? And to answer these questions, we need to get a better understanding of the permafrost thermal regime really in steep terrain on Svalbard. Because most permafrost measurements that we have from Svalbard are in shallow, in flat terrain or in gently sloping terrain. So there are lots of boreholes, but most of them do not represent like the steep terrain. And the steep terrain, of course, features a lot of like variations in the permafrost thermal regime. And to address this limitation, we placed ground surface temperature measurements along the west coast of Svalbard. So in Hornsund, at Forkastningsfjellet, and the Brøgga Peninsula, in steep terrain, in different altitudes, in different aspects, different slope angles. And, but we placed them only last summer, so we will, for the most of the field site, first retrieve data next summer. But for some of the field sites, we already have some data. For example, here again, Forkastningsfjellet. So you see here all the yellow dots are ground surface temperature measurements, and the numbers are mean annual ground surface temperatures. And you see that the field site here, that's about like 1.5 kilometers. But we have a huge variation of ground surface temperatures. So you see here close to sea level, we have minus 1.4 degrees. And then here at higher elevation, minus 3.6 degrees. So we see the strongest dependency here is really on the altitude. The higher we go up, the colder it gets. But we also expect that, for example, slope angle and aspect play a role, snow conditions, ground properties, and the latitude. And we will look further into that once we have data from from the other field sites as well. So I want to conclude here with some open questions. So the first one is, so how does the thermal regime really vary in steep terrain on Svalbard? And to answer these questions, we will continue to analyze this logger data that we will retrieve next summer and continue with them. Also more field measurements would be helpful. And we plan to do some high-resolution permafrost maps based on the cryogrid model that you heard from Sebastian. So on his last slide, he had this high-resolution map from Gaustertoppen with the 5-meter resolution, and something similar could be also an option here for Svalbard to extend like into areas where we don't have measurements. Another question would be what processes control the slope destabilization at Forkastningsfjellet, so especially for like these deep-seated rock slides. Also here, extended field measurements would be helpful, for example, like ERTs across the sliding plane to see like how is the thermal regime within the sliding plane, modeling of these processes, and to what extent is the rest of Svalbard as well prone to landslides. So here some mapping campaigns or remote sensing could be helpful, as well as modeling with cryogrid, where we are currently developing a module which allows us to assess slope stability for shallow landslides for the model on like a spatial scale. And if you want to discuss these questions, I'm happy to do that. So just come to me here at the conference or write me an email. Thank you.
Thank you very much, Judita. We have questions for, we have time for a very short question. If there's, yes, quick.
So the block itself, it should be frozen, but the sliding plane, it looks like there are hydraulic pathways, so that we see some permafrost degradation in the sliding plane, but the block itself, it stayed as well very intact while it was sliding down. So we expect that, so the block itself was frozen, but not the sliding plane.
Thank you very much. We will learn more in not this talk, but the next one. But now we will go to soil, and we will listen to Sylvain, who's going to teach us about active layer microbial activity and how it varies across different permafrost soils from the university here in Tromsø. Welcome.
Oh, thank you. So yeah, I'm a researcher at the Tromsø Museum here, and I'm going to go at a much smaller scale in terms of permafrost processes. So I don't really need to talk to you about why permafrost is important, carbon feedback, etc. But perhaps why look at microbes is worth a bit of discussion. Permafrost is usually presented as a very extreme microbial habitat because of a lot of constraints on microbial growth, which means that in general in permafrost you have no fauna that is living, you have very few fungi that are viable, and mostly bacteria and archaea surviving there. Now what it means over long periods of time that these microbes are frozen into the permafrost is that there is no possibility of dispersal from the outside pool of microorganisms. So even though you have very high microbial diversity in soils, you can over long periods of time lose lots of taxa, which might eventually mean loss of functions. This has been observed in terms of methanogenesis. It has also been observed in terms of CO2 production and nitrification. And in the field, it has also been linked to nitrous oxide emissions. Now, all of these evidences came from Jedoma deposits, which are among the oldest permafrost deposits. So they don't cover a very large area of the permafrost region, but they store significant amounts of carbon. However, the fact that they are very old means that they have been exposed to these constraints for a very long time, and that they have extremely low microbial metabolism when you thaw them. So they might not be representative of all permafrost soils. What we wanted to ask here was whether this loss of function also happens in more recent Holocene permafrost deposits. So for that, we compared Jedoma soil from the Krell Tunnel in Fairbanks to 3 other permafrost soils. One was an unsorted circle from Alaska, very mineral soil, and then 2 types of peat, sage peat from tussock tundra and sphagnum peat from Epalsa. We inoculated these soils with microbial suspensions made from their own active layer to simulate what will happen when thaw water percolates through the soil and inoculates newly thawed permafrost. And we compared that to negative controls, which had received no additional microbes, or a positive control, which was made from a temperate grassland as a very multifunctional community. We incubated these soils for about a year. We measured CO2 production, bacterial communities, some nitrogen cycling genes, and a range of soil chemistry parameters. And the results I'm going to show you all look pretty much like this. We have gray dots for the negative control, so the permafrost on its own, black dots for the positive control, the permafrost inoculated with the temperate grassland, and colored dots for the different active layer microbial suspensions. So in terms of CO2 emissions, we could see that all of the soils, no matter their age, responded very strongly to the positive control. We had between 20 and 60% increase in CO2 production over the course of 1 year. But when it comes to the active layer inoculum, it was quite a different picture. And in only one of the 3 permafrost soils from the Holocene, we could see a significant increase. However, they all increased the production in Jedoma permafrost. We then looked at bacterial communities, and you can see that the picture is pretty clear in terms of what happens here. I can dump it down to something a little bit easier to interpret. This is microbial diversity, so the number of species, so to say. And we could see that in one soil, we had an increase only with the positive control. In another soil, we had an increase with the active layer community and the positive control. And in the Jedoma soil, we had differences all over the place. Now, I only show you diversity, but the community composition in itself also changed and that matched these patterns in diversity. If you remember the CO2 results from just before, you can see that the results in terms of microbial diversity are strikingly similar to these results in terms of CO2 emissions. So we interpreted this as rather strong evidence that the microbial communities in all of these permafrost soils was limited by lack of functions that could be restored by new microbial communities. So it's not just Jedoma because it's particularly old, it's also more recent permafrost. We looked at nitrogen cycling, and here again you can see that the picture is pretty clear. To summarize it, we didn't see any nitrifiers in any of these permafrost soils unless we added them through the inoculation by the temperate grassland soil. When there was no nitrifiers, it also means there was no nitrate. We only saw nitrate when the temperate grassland soil was added, and consequently we only saw nitrous oxide productions when this inoculum was added. So it seems that nitrous oxide production is limited in all of these soils, also by the lack of nitrifiers. For one of the soils only, we did anaerobic incubation for 6 months. We took the pulsar soil from Abisko, and we compared negative control with live active layer inoculation, measured CO2 and methane over 6 months, and saw quite a big decrease in CO2 emissions, about 30%. And so an absolutely massive increase in methane emissions by 400%. So we calculated CO2 equivalent to have an idea of how that affects the global greenhouse gas balance of this soil. And we ended up with about 35–40% increase over the course of 6 months. So this is a soil that was already producing methane. If you incubate it on its own, it produces methane. But if you add more fresh methanogens, it produces more methane. So this is something that might be important to take into account because this is pretty recent permafrost. It's not old, the pulsars from Abisko. So to summarize, we wanted to look at whether loss of function is only something that happens in very old Pleistocene permafrost, and whether active layer microbial communities could restore these missing functions. We saw that all of the permafrost soils were missing some functions. CO2 was a very clear case, but the others were also missing nitrifiers, for instance. We saw that restoring missing functions only occurred in the events where microbial communities were actually able to establish into this permafrost. So that's what is called community coalescence, when two microbial communities form a new one. And this was not always the case. Active layer microbial communities were not as efficient in restoring function as temperate grassland community. That was both because in some cases they lacked functions. For instance, they also didn't have nitrifiers that were able to establish. But also in some cases, they were not able to establish into the permafrost themselves. So for future directions, we think it's important to look into what drives the lack of functions in active layer microbial communities and whether this is something that is likely to change in a warmer Arctic. We also need to understand better how and why community coalescence happens or doesn't happen when permafrost thaws and active layer microbes get into contact with it. And only when we have a better understanding of this will we be able to incorporate these dynamics into modeling exercises. But the main take-home message is that if we're going to do more incubation studies, we need to account for microbial dynamics. And this has really changed quite a lot already in the last few years. So it's, yeah, good progress being done here. Quick thank you to all of the co-authors, the funders, and the institutions, and I'm happy to take your questions.
Thank you very much. We have time for questions from the audience. Sebastian, you can go first when you get a mic.
When you talk about the microbial dynamics, do you think it's a problem also on timescales longer than the 1 year incubation? So basically like 1 or 2 decades, which is really like relevant, like post-thaw? Is it to be expected that something could take that long to re-establish?
I think that's actually a 1 year incubation at 10 degrees in the lab is pretty much matching a couple of decades in the field, or even perhaps longer, because it won't be 10 degrees down at the thaw front. So it will be rather short seasons where it's thawed and at lower temperatures. So it's not really clear how realistic it is, but it's probably relevant to quite long time scales in the field.
Yes, in the back.
Did you also look at denitrifiers or only nitrifiers?
We looked also at near genes and nose genes, and there they were actually present all across the board, even in non-inoculated permafrost. So the limitation on nitrous oxide production is not later in the denitrification. It seems to be really the lack of nitrates and the lack of nitrifiers to produce it.
And one last quick question, maybe? Then I would like to ask you one thing.
Yep.
What about landforms and this? I mean, you talk about lots of, we could call them PG landforms. Do we dare to ask what would happen if you did the same thing in active layer permafrost that is not organic rich?
We had one that wasn't organic rich. It responded only to the positive control. The problem is the DNA data we got from this cryoturbated soil, which was, I think, maybe 1% organic matter. The DNA data was really bad because of very, very low microbial biomass, so it's quite tricky for us to interpret it. We will need to look a bit more into it.
That's also a good idea. Thank you very much. And then we will move on to the last talk of this first session. This is now going to be given by Gøran Eishan from the Geological Survey of Norway. And now we're going to learn something about INSAR. So now we go really into remote sensing. And he's talking about something that's being launched this week, which is a new INSAR service of all of Svalbard. What a talk to end with.
Thank you. Hi, I'd like to introduce you INSAR Svalbard. It's a new satellite-based ground motion service for Svalbard. And it has been developed by the consortium of NORS, Norwegian Geological Survey, and Space Agency of Norway. And also with the close collaboration between local stakeholders, municipality, researchers, agencies in Svalbard. So this service basically allows us to monitor the ground motion at the surface of the Svalbard, especially the areas affected by permafrost thaw. And in a rapidly warming climate, of course, understanding how ground is moving becomes increasingly important. So what do we mean actually by ground motion in Svalbard? So as you know, there are several factors that controls the seasonal processes in Arctic terrain, like climate, vegetation, snow, sediment, rock, ground temperature, and of course water and ice presence in the soil. And all these parameters are controlling the seasonal processes, such as frost heave in winter, thaw subsidence in summer, and downslope creep. And all these movements are subtle and widespread in the Arctic terrain. From a research perspective, understanding these movements are valuable because they tell us how the ground is responding to the changing warming climates. And from a management perspective, they are also matter because they affect structural stability, and in certain cases also contribute to landslides or geohazard activities or slope instabilities. So that's why understanding how, when, and where these movements are happening is not just important for science, and also for practical reasons they are valuable. So we use radar satellite technique. So in this technique, satellites send signals to the ground and records the echoes that comes back to the satellite. And when we take several repetitive images over the same area, we can measure how this distance between ground and satellite is changing. So when we know this distance change over time, so we can find the deformation or ground motion, relative ground motion evolution through the observation period. So some of you might be familiar with INSAR Norway that has been operational since 2018, and we have been using it for monitoring landslide, unstable slope, infrastructure, and also for operational purposes like in geohazard activities, studies in entire Norway. And there are Sentinel data, as you know. With the Sentinel data, we have detected so many new unstable slope after the launch of this service. Similarly, there is also another service very parallel to this that covers entire Europe. It's called Copernicus European Ground Motion Service, EGMS. But as you see in both services, there is Svalbard which is missing, and there is two main reasons why Svalbard is missing, because there is a unique technical challenges. It is covered by ice and snow for longer term, and the surface movement is more seasonally behaving differently than the mainland, in the most of the mainland in Europe. So, and also another limitation, the user need is different here. So when we develop this service, we always work with the local stakeholders and listen their needs. And there was always iterative close collaboration during the development of this product. So this web page is activated just maybe 1 hour ago. So I invite you to to visit maybe after the presentation or now. So this is the main MapViewer.js platform. As you see, there are 5 pilot areas: Longyearbyen, Ny-Ålesund, Svea, Hornsund, and Kapline. These areas were selected based on scientific and societal importance. Settlement, there are research institutions, cultural heritage sites, and as you see, you can also see like different menus where you can activate and deactivate different backgrounds, and we have a toolbar where you can visually play with the data, download the data, take profile, and visualize time series, etc. And also visualization setting here. Now we will zoom on to Longyearbyen, one of the study areas. As you see here, the same area, but at different time scales information. Here we have 2 different products. One of them seasonal product, the another one interannual product. The seasonal product, in seasonal product, we map the maximum displacement during each season. So each seasons are snow-free data. We use only snow-free data. Each seasons are processed separately, and they are starting from 0 from the beginning of the observation period. So each season, if we have 5 years, there are 5 independent measurements that start from the beginning of the snow-free season in the relevant year. And when it comes to interannual products, we use entire season snow-free data, and we see more long-term movement, not seasonal, but long-term movement of the ground deformation. Now we will zoom on to see more detail. Here, again, we can see the seasonal on the panel A and interannual on the panel B, and also time series taken from some specific point over each product. So as you see, for example, this point, green circle, represents the time series are representing here, this one. So as you see, it's more stable, and then there is a little acceleration, and we map the maximum deformation. This map shows the maximum deformation of each point. Another bullet point here, as you see, there is a towing motion, and at certain point, it reaches its maximum, and then freezing again, so it's rebounds. So here we map the maximum absolute deformation, which this map shows. So this seasonal product mainly captures the tau subsidence and frost heave effect. And interannual product, when we look at interannual product, we can see the long-term pattern of deformation taken from different points. Here, as you see, how we can map how the point on the surface is moving in longer term. The next slide. So yeah, the application areas and future directions in this project. So this product has potential applications areas include monitoring permafrost, tau, and subsidence, to estimate ground ice distribution, to assess terrain stability for infrastructure, especially in cities, in towns where we have residential area, research communities, or infrastructure like airports, and also cultural heritage sites. There are also some of them in Svalbard. Detecting slow-moving slope and shallow landslides, mapping glacial forefield evolution and sediment dynamics. And when it comes to future direction, it will be updated regularly using Sentinel-1 data every year. And for now, it focuses on only 5 pilot sites. And in the near future, the plan is extending it in a more pilot areas and with the intention to cover entire Svalbard. There will be more new approach to develop the processing strategies, including automation, filtering procedure to increase the robustness of the data and the quality. New satellites also will be included here because this year NISAR is now covering the southernmost part of the islands, and in coming years there will be another satellite, radar satellite, SARB, ROS-L, developed by European Space Agency. It will cover the entire Svalbard. So this will bring new opportunities, and in terms of filling the gap in the product, it will be a big contribution also in the near future. And also maximizing the societal and scientific value of the product with the close dialogue with the local stakeholders. So this is the plan for the future. And so just last example from the long-year buoy. As you see here, this shows the seasonal product of the one, or if you can visualize the time series of 1 point, or you can plot a polygon that covers the several points. Yeah. So you can see how seasonal product is visualized, each starting from 0, and you can see how during that snow-free season it shows the pattern, and also permafrost creep from other area. So yeah, thank you for listening. That's all from my side.
Thank you very much for introducing this new service. It's going to be very nice to see that. Unfortunately, we used all our time in this first session, but if you remember what I said in the beginning, we will have some time for more questions and interactions towards the end of the following session, because now you have a coffee break, and then we start again in here at 11 o'clock. We will run 6 oral presentations, and then we will have more questions. So please come back, enjoy your coffee break.